What's that? Yes, I got a new projector. It's brighter, but it's not quite as big. That's as big as it gets. And they said, the district said, these are the projectors you get. Doesn't matter if it doesn't fill the screen. Those are the ones you get. So. All right, so we're in section 14.4. Center of mass and moments of inertia.
It's a lot more blue.
It's a lot bluer, yeah, and it's bright. I can have the blinds open with the projector going. All right, so we have defined so far. We've defined a double integral as the limit as delta A approaches 0, and we said we were being loose with our terminology here, of the sum I equals 1 to n did I put too many m's in here? Moments. All right, so we defined our a double integral as this limit, the limit of this sum. And so far we've said that the f of x, xi, yi that we've used is it represents a z value, a function, a height above the xy plane. So this double integral is a volume. That's what we've been talking about so far. So for the next couple of sections, we're going to use other functions in here in this sum and let the double integral represent something other than a volume. And the first thing that we're going to talk about is mass and center of mass, and a couple different kinds of moments. So if we talk about, we're talking about planar lamina again. So we have a little section of some material here in the xy plane. And we're saying that the mass of this is, this little piece is m sub I. So we're talking about our mass. And our coordinates here are y sub I and x sub I of this little section of this material. And we're going to say that the mass per unit area is rho. And rho can be a function of x and y. So the mass of this little piece of material, whatever it is, m sub I, is going to be rho at that particular point times delta A sub I. And if we have some region defined in the xy plane, we're going to sum these masses over that region to get the total mass of the planar lamina. So we make the sum of rho x sub I, y sub I, delta A sub I. Well, that exactly matches our definition of a double integral. So the mass of this plane region and our region is R, will be, M is going to be rho times the area, which is going to be the double integral over our region of rho xy times dA. So we can have a variable mass density, mass per unit area, and we can find the mass of some planar region that has a variable mass density by evaluating a double integral. So what we've done here is take this, rather than having a z, a height above the xy plane, our function here is our density function. And it fits exactly with our definition of a double integral. So now, rather than a volume, we're going to perform a double integral and get a mass. And we're going to use the same process to talk about our moments. Moments about the x-axis, moments about the y-axis. We're going to turn those into double integrals. So questions on our starting assumptions here. All right, so let's look at setting up one of these integrals. So let's say we want to find the mass. Region bounded by x greater than or equal to 0, 0 less than or equal to y less than or equal to 9 minus x squared, and rho equals, our mass density is xy. So we're going to go through the same process. We want to sketch our region. This is our function that we're putting in our integral. So let's sketch our region. Here's our xy plane. X is greater than 0, and 0 is less than or equal to y, less than or equal to 9 minus x squared. So what is y equals 9 minus x squared? Upside down parabola? So something like that, right? And x is greater than 0, greater than or equal to 0. So this is our region. So we can set up our double integral. This is not too bad of a double integral. So our mass is going to be the integral. Which way do we want to set our integral up? Vertical. So our little rectangles are going to go this way. So y is going to vary from 0 to 9 minus x squared. X is going to vary from 0 to, what do I get down here? When y is 0? 3? 0 to 3. And my integral would be xy dy dx. So this one wouldn't be a tough one to evaluate. We just end up with polynomials here. So we end up with a y squared over 2. We'd be squaring 9 minus x squared, and then we'd evaluate that. X times that, evaluate from 0 to 3. So we'd end up just evaluating integrals involving polynomials. So that wouldn't be a tough one to evaluate. Hopefully not tough. So questions on the setup there. So really, we're doing the exact same thing that we've done before. Now our function here is, rather than giving us a volume, this is going to give us a mass of this region. And our mass density is varying with x and with y. Well, the other thing that we did during first semester when we talked about mass and planar lamina is we talked about our center of mass. So our moments and center of mass. So let's talk about that. And I'm just going to write COM for center of mass. So we have the same setup here. We have this region in the xy plane, some region, and we're breaking it up into little sections, and we're at y sub I here and x sub I here, and we know that the mass of this little piece is rho. I'm going to write this down here. Times delta A sub I. So the mass of that little piece is rho times delta A sub I. Remember, we defined our moment about the x-axis, and the moment about the y-axis is the mass times its distance from the axis. Well, now that we can do this with a double integral, we can do multiple integration. Our moment about the x-axis is just this mass times its distance from the x-axis. So m sub I, y sub I is the moment about the x-axis. We're just multiplying that mass times its distance from the x-axis, and that's going to be rho at that particular point times the area at that particular point times y sub I. And the moment about the y is just going to be that little mass, m sub I, times its distance from the y-axis, which is x sub I, and that's our density. And we sum the moments of the individual masses over the region, and I forgot to write, there's my r, over the region, and we sum those moments to get the moment of the entire planar lamina, the entire region. So we just add all these together. Well, this sum, when we sum this over the area, let delta A sub I approach 0, that sum exactly corresponds to our definition of a double integral. Rho x sub I, y sub I is some function of x and y. We multiply that by y, that's still a function of x and y, so we end up with a double integral. So we're going to say our moment, we're going to define we call this our moment, and I got the right number of m's in there. Moment, we'll also hear it called moment of mass, because a moment is something weighted by its distance from an axis, so this is the moment of mass. You'll also hear it called the first moment of mass. We'll talk about the second moment of mass in just a little bit. So all these terms mean the same thing. With respect to our x-axis, m sub x is the double integral over our region of y rho xy dA. And about the y-axis is, we write m sub y, that's a double integral over our region of x rho xy dA. And then our center of mass is exactly the same as we used before, and I'm just going to say we'll abbreviate COM. x bar, y bar is m sub y over the mass for my x coordinate and m sub x over the mass for the y coordinate, where m equals the mass of region. And if we think back to how we had to do this when we were performing a single integral, this is a much easier setup. With a single integral, we had to make some assumptions. We had to assume that the mass was concentrated at the center of a rectangle. We had to find the distance of that center from the x-axis. We had to find the average value of the function. We had to add the two values and divide by 2 to get the center. And we had to perform those integrals. We had to make those assumptions in order to perform those integrals. Here, we just find our density function. If our density is uniform, then rho is just going to be 1, and my m sub x, moment about the x-axis, is just going to be the double integral of y dA over the region. If our density is uniform, m sub y is just going to be the double integral of x dA, and we can perform that double integral over our region. So much easier to set up our moments and center of mass with double integrals. And I've got my r here over our region. And just again to talk about terminology, center of mass is usually a property of the material because the density can vary. When we talk about the centroid, sometimes we talk about the centroid and the center of mass interchangeably. The centroid, for the centroid, you're assuming that the density is constant. So the centroid is a property of the shape. So a triangle always has a particular centroid if its density is uniform. Center of mass usually is referring to a region where the density can be variable. So the center of mass is a property of the material as well as the shape. Centroid is usually just a property of the shape. All right, so questions on our definition here and how we came up with this. It's kind of nice we just follow the same procedure for the different things that we want to do with a double integral. And now that we know what a double integral is and how to evaluate it, we can set this up pretty easily. So we'll do an example. After this, we'll talk about the second moment of mass, which is the moment of inertia. And then on block day, we will use this idea of a double integral to talk about the surface area of a surface bounded by a region in the xy plane, which is kind of nice. All right, so no questions? Okay. So let's do an example. We want to find the mass and the center of mass. And our region is bounded by y equals x to the third, y equals 0, x equals 2, and rho is kx, where k is just some constant. So let's sketch our region. Let's see, so here's x equals 2, y equals x to the third, so that's going to look something like that. And we're bounded by y equals 0, so here's y equals 0, x equals 2, and y equals x to the third, so here's our region. So we can set our representative rectangles vertically or horizontally. I usually choose vertically, so there's my little representative rectangle for our double integral. So let's set this up. Our mass is just going to be the double integral over our region of rho dA. So our integral is going to go from y equals 0 to x to the third. X is going to go from 0 to 2 of kx dy dx. Nice easy integral to evaluate. Oh, it looks like it's windy outside. See the screen maybe? So this nice easy integral to evaluate, we just end up with a polynomial. When we evaluate this out, this comes out to 32k over 5. And m sub x, moment about the x-axis. We have our region set up. We know our density. All we have to do is stick our distance from the x-axis into our integral. So we get the integral from 0 to 2, 0 to x to the third, kx y dy dx. And because our density function is nice and easy, not a complicated function, these integrals don't turn out very complicated. They're not always this easy, but in this case they do turn out that way. So another one, nice and easy integral to evaluate. We just end up with polynomials. This comes out to be 16k. And m sub y, we have our region, our integral set up, our limits, everything stays the same, 0 to x to the third, and we just stick our distance from the y-axis in there. So we get kx squared dy dx. Another one that's not too hard to evaluate. And we end up with 32k over 3 for this one. So our x bar is m sub y over the mass, and we get 32k over 3 over 32k over 5, which comes out to be 5/3. And y bar, m sub x over m. So we get 16k divided by 32k over 5, and we end up with 5/2. And whenever you do these, find these center of mass, make sure that the numbers you get make sense. So our density is increasing as x increases. So our center of mass should be kind of pushed over towards in the x direction a little bit. So 5/3 makes sense. 5/3 is, if we got something bigger than 2, we'd know we'd made a mistake. And y is 5/2. So it seems reasonable that those numbers seem reasonable for a center of mass for that particular region. Questions on what we did there? So this just gives us another reason to put things into double integrals and do double integrals. And that's always an exciting thing. All right, let's talk about the second moment of mass. So the first moment of mass will give us our center of mass. So our first moment of mass we use to find our center of mass. So second moments. So our second moment, is just, we're waiting the second moment of, and I'm going to write second moment of mass. That's really the only second moment we're going to talk about. So now instead of multiplying the mass times its distance from the axis, the second moment means we multiply the mass times the square of its distance from the axis. And I'm just going to write distance squared. So we're weighting this mass by the square of the distance from the axis. What the second moment of mass, the other name, the more familiar name for second moment of mass is moment of inertia. And moment of inertia is important because it tells, the moment of inertia is a measure of the tendency of the mass whatever the region is, to resist change in rotation. So our second moment of mass is used to tell us how that object is going to resist changing rotation. So that's why it's important. We can go through the same process that we went through for the first moment of mass to define our double integral. So we're going to define our second moment of mass. I'm not going to go through the process again. I think we're familiar enough with the process now. Define the moment of inertia. Or the second moment of mass. And about our different axes. About the x-axis. And we say I sub x is going to be the double integral over our region of the square of the distance from the x-axis, y squared, times our mass. And about the y-axis, I sub y, we're going to take the double integral over the region, the square of the distance from the y-axis, x squared, times our density, times our area for our mass. And then because we're talking about we're working on a double integral, we call the sum of these two, I sub x plus I sub y, we call I sub O. And we can also write this as the double integral over our region of r squared, rho dA. And we call this the polar moment of inertia, or the second moment about the z-axis. So we can talk about the region rotating about the z-axis here as well. So that's our second moment of inertia. And then the quantity that has to do with moment of inertia that's kind of analogous to the center of mass, we call the radius of gyration. So just let me make sure everybody's good with what we're talking about here with the second moment. We set up our integrals the same way. We defined our region in the xy plane. We're putting our density function in here. We just put an additional x squared or y squared into our double integral to evaluate the integral to find our second moment about the x-axis, about the y-axis. And we can use those to find the polar moment of inertia. And usually it's easier to find these two and find the sum to find your polar moment of inertia than it is to evaluate this integral. Usually it's easier to find the two individually than to do this together. So then the radius of a gyration is kind of the quantity that's analogous to the center of mass that has to do with the second moment. So let's define our radius of a gyration. Our radius of gyration is, and the radius of gyration is going to be our double bar is the square root of our moment of inertia divided by m. So our x coordinate of our radius of gyration is the square root of I sub y divided by m, and the y coordinate of the radius of gyration is the square root of I sub x divided by m. And what the radius of gyration tells us is that if the entire mass were concentrated at a distance r bar from the axis of revolution, so if our entire mass is concentrated at that distance, it would have the same moment of inertia as the system, as the entire system, rotating about the same axis. So when we're talking about center of mass, what we can do with center of mass is when we're talking about that region moving, we can assume that all the mass is concentrated at the center of mass, and that simplifies calculation. If that region is rotating, we can assume that the mass is concentrated at the center of gyration, and we could treat the system as if the entire mass is concentrated there, and then do our calculations that way, and that simplifies that way. So that's why the radius of gyration can be useful. We can assume that our entire mass is concentrated at that point, and it's going to behave the same as the entire system rotating about the same axis. All right, let me figure out which example I want to do this one. Okay. So let's do one example of setting up the integrals. We're not going to calculate all these. We're not going to evaluate all these integrals. And a lot of these, what I will do, because with center of mass, with moment of inertia, there are multiple integrals. I would ask you on a test, I might say, like we did last semester, set up but do not evaluate the integrals for these things, and then evaluate the integral for whatever, I sub y. So you'd set up your integrals, but you'd evaluate one. Because there's a lot of stuff involved in the setup. All right, questions? All right, so let's set up one of these integrals. So we want to find I sub x, I sub y, I sub 0, x double bar, and y double bar. And our region xy such that y equals x squared, y squared equals x, and our rho is x squared plus y squared. And I guess I didn't set up my region. I should say, let's say I was trying to be fancy here. Our region is bounded by. So I'm going to say bounded by. The way I wrote it before, the region would only be those curves. All right, so let's sketch our region. In the xy plane, y equals x squared is here, and x equals y squared. I get a parabola going sideways, like so. So my region is right in here. So the boundaries of my region, the two curves intersect here at 0, 0. And where do they intersect here? What's this point? 1, 1. So and this is 0, 0. So that's our region of integration. So our mass, our integral for the mass, is going to be the integral. And I'm going to set my rectangles because my preference is to set them vertically. Double integral x equals, or y equals x squared to, what's my upper limit of integration? Y, if I set my rectangles here, it's varying from x squared to y squared is, as a function of x, square root of x. And then x is going to vary from 0 to 1. And my mass is just my density, x squared plus y squared, dy dx. So that would be my integral for the mass. And this one, because we have the y squared, this one it's not a particularly difficult integral to evaluate. So we're evaluating y squared from x squared to square root of x. So we end up with polynomial. We end up with familiar functions that we're integrating here. I sub x, the second moment about the x-axis, moment of inertia about the x-axis. Our integral is set up here, 0 to 1, x squared to square root of x. And our second moment of inertia about the x-axis, we put in a y squared. Our density, x squared plus y squared, dy dx. Again, not particularly difficult integrals to evaluate. We just end up with polynomials and powers, rational powers of x. So not particularly difficult integral. Just power rule stuff. And I sub y, same region, 0 to 1, x squared to square root of x. And then we put our square of our distance from the y-axis, x squared times x squared plus y squared, dy dx. And once we have all three of these, we have everything we need for the other integrals. I sub 0 is just going to be the sum of these two. Once we evaluate these two, find the sum. And usually that's how I would suggest you do it. Find them individually and then find the sum. And then x bar is going to be the square root of I sub y from this integral over our mass from this integral. And y double bar is just going to be the square root of I sub x over the mass. So once we have these three, these are the three integrals that we need for everything else. And we would evaluate these. Not difficult ones to evaluate. Questions? Okay, so we're just following the same procedures that we've done before, setting up our regions. We just have other things that we're putting into our integrals to evaluate. So it's just a tool to let us find other things with a double integral. And then on Thursday, we will talk about using a double integral to find the surface area of a surface, like I said, bounded by a region in the xy plane. Friday, we will then finally start talking about triple integrals. And that's when things get really, really fun. And we have just passed into out of the triple digits and into the 4-digit numbers in our pages.